now I want to look at a specific type of modeling. I want to look at modeling with functions that are first-order polynomials. So recall that we say a function is a polynomial of degree 1 or order 1 if it can be written as ax plus b. Right? So this is another way of saying I want to plot functions that are lines. So this is linear. So the picture for these functions will be something like the following. I have my input variable x, and I'll write input here just to remind you of this is a nice way to think of functions as inputs and outputs. And then I have f of x here, which is my output. And the plot for this will be just a line. So maybe something like this. So what kinds of things are reasonable to model this way? Well, it typically depends on how the situation is worded. You have to read the kind of context of the relationships and try to infer that they're linear. So here's an example. Let's say we have a factory and we're trying to build widgets. A widget is just sort of a word that economists and business people use to say, well, it could be any object. I don't really care what it is, so I give it this silly name called widget. So what we are doing is building widgets. So suppose the cost of building widgets is $20 per widget plus a fixed startup cost of $1,000. So you can think of this as I had to pay $1,000 to get all the tools I needed to make any widgets, and then after that, it still costs $20 per widget to make. So what we want is a function of the number of widgets that is the cost of making them. So goal c of x, a cost function for x widgets. Now I set this up so that this makes sense as a linear function, right? Because I know that it costs $1,000 just to start manufacturing them at all. So you can think of this as a fixed cost. And then for every widget that I make, I pay $20. So as a function of the number of widgets, the cost is 20 times the number of widgets, x, plus 1,000. So c of x is 20x plus 1,000 in dollars. Okay? And of course, this falls into the linear regime. So this is a linear function. And in fact, we can interpret it as having a slope and a y-intercept. The slope in this case is equal to 20, and the y-intercept is equal to 1,000. So this sort of gives us insight into what types of problems admit linear functions. Well, in this case, we had a fixed startup cost, 1,000, and then for every additional unit, I just had a fixed cost of 20. So it's somehow a simple model. I don't really benefit if I make, one widget versus a million widgets. In general, it's easier to make a million of something than it is to kind of make just a smaller number. You get benefit from that. This is called economies of scale. But in this case, we don't even get that. It's sort of a very, very simple model, which is why it's sort of described in this very simple way by this linear relationship. So not the most sophisticated way of describing something, but it is a nice tool to know, especially if you're interested in economics. I mean, this is a very good economic example. And then you should also think in terms of the CLEP. This is a very nice thing to ask you about, to be able to go from a word problem to the function, and also to interpret it in terms of slope and y-intercept.